Good afternoon, everybody. Thank you for coming. My name is Max Ross. I'm a software engineer on the App Engine team at Google. I focus primarily on things related to persistence. I work on the App Engine Datastore, the common piece of infrastructure that's behind persistence for both the Python and Java runtimes. I also work on the Java low-level Datastore API, and I also work on the JDO JPA implementation that we provided for persistence in Java. And today we're going to be talking about the softer side of schemas. So before we jump in, let me give you a brief overview of what you can expect from today's talk. Just quick show of hands. How many people here have already built and deployed an application on App Engine? All right, lots of hands. And how many have done Python? And how many have done Java? All right, I like to see all those Java hands. That's great. Okay, so just to make sure that we all have the same foundation, I'm going to spend a couple of minutes talking about some of the fundamentals of the App Engine Datastore, and then we're going to build on top of that. From there, we're going to move to a discussion of soft schemas, and obviously I owe you a definition of that term, and I will provide one. But we're going to talk about soft schemas and how you can use existing Java persistence standards, specifically JDO and JPA, to implement a soft schema on top of the App Engine Datastore. And then we're going to go through some strategies for migrating existing applications onto App Engine, and then some strategies for moving App Engine applications off of App Engine. Not that you would ever want to do that. Actually, we know that you would want to do that, and that's why we've put a lot of thought into making sure that that's going to work nicely. And then we'll finish up with some questions. So let's talk about the basics of the App Engine Datastore. First and foremost, it is transactional. It has the ACID properties that we have rightly come to expect from something that does persistence. A little bit more interestingly, it is natively partitioned. So the App Engine Datastore is a distributed system. Your data is split out across a network of servers. And unlike an architecture where you have horizontally partitioned your data and maybe it's the responsibility of your code to decide at runtime where data is going to go, the App Engine Datastore is natively partitioned. We're going to split your data up for you. So just by building your application on top of the Datastore, this is going to happen. That's pretty cool. Another interesting aspect of the Datastore is that it's hierarchical. Every entity that you store in the Datastore can have a notion of its parent, or its grandparent, or its great-grandparent, or it can be one of these entities that we like to call a root entity where it doesn't have a parent at all, but this is baked into the Datastore itself. It's a native feature. Another interesting aspect, it is schema-less. So the Datastore does not have any notion of the structure of your data. And we're going to talk a lot more about this as we go forward. And then finally, it is based on Bigtable, which is a distributed storage system that Google has developed over the years that we run for you. A couple of things that I want to point out that the Datastore isn't. It isn't a relational database. And I really want to make this point clear. The Datastore isn't a relational database. It's not a SQL engine. In this talk, we're going to be discussing how JDO and JPA, these Java persistence standards, which are commonly used to talk to a relational database. We're going to talk about how these persistence standards can also be used to talk to the App Engine Datastore, but that does not mean that the App Engine Datastore is a relational database. So here's a quote from my friend Z, who I sometimes ride the Google bus with up to San Francisco. We were talking about App Engine one day, and I was describing the Datastore to him, and he said, "I don't want a relational database for my application. I just want persistence." And now I know not everybody in this room is going to agree with that sentiment, and it makes sense that some people will agree and some people don't. But I want to say that for those of you that agree with Z, you're going to be really excited about working with the Datastore because it really does simplify things. One of our primary design goals here is to simplify storage. We want to simplify the development of applications that require storage, and we want to simplify the management of applications that require storage. Now, the reason our solution looks the way it does is that throughout App Engine as a whole, the entire product, we sort of have a history of taking existing infrastructure services that already exist within Google. These are the types of services that allow you to send mail. These are the types of services that allow you to fetch the contents of a URL on the internet. We have a long history of building these services in a way that scales and in a way that we know how to manage them very efficiently so that the people who consume these services don't have to worry about managing them efficiently. Sorry, distracted by beeping. The data store is no different. So, why are we exposing Bigtable? We're exposing Bigtable because we're really good at running this service, right? And this is a big part of simplifying the management of applications that need storage. So, for those of you who might be thinking, well, I've heard that Bigtable is a storage solution for applications that need to scale to Google scale, to the size of Gmail, for example. I'd like to try and make the point that no matter what type of application you're building, scale always matters, right? It might not need to scale to the size of Gmail, but you have some target scale in mind. It might be 5 concurrent users or 20 concurrent users or 100 or 1,000, but every single one of those targets involves certain design decisions that you need to think about. So it's not just that App Engine is for building applications that need to scale to the same size as Google applications. It's for building applications that are going to scale to whatever that scaling target might be more easily. That's one of the things we're trying to simplify here. So let's look at the storage model. The basic thing that we are persisting here is something called an entity. And an entity has 4 components. There's a kind, which for those of you coming from the relational database world would probably think of this as the table. It has a key, which you can think of as the primary key. There is the entity group. This might be, and there's the entity group, which is part of every single entity, and this goes into determining what partition your data is going to live on. If you've done horizontal partitioning before, or sharding as we like to call it, this term will be familiar to you. We use this to figure out what data this entity is co-located with. And then finally, you have some number of typed properties, which you can think of as columns. So here we have an example where the person is a kind, and if you'll notice here, the entity group and the key are the same. Anytime you see an entity where the entity group and the key are the same, that means you're looking at a root entity. It doesn't have a parent, right? We talked about the data store being hierarchical before. If the entity group and the key are the same, it doesn't have a parent. It's a root entity. And then in this example, we have 2 properties. We can see that Ethel is 30 years old, and Ethel has a best friend named Sally. This bottom column here, the best friend, you can see that it's referring to another key. You can think of that, if you're coming from the relational world, as a foreign key, right? The data store does support this. So let's talk about some of the interesting features that you get with the data store that you might not be accustomed to. First and foremost, there is this hierarchical nature of the data store. In the top right-hand corner here, we have the same person as before. We have Ethel, whose best friend is Sally. But then on the bottom, we have a person entity that is a child of Ethel. And the way that we know that this person entity is a child of Ethel is we can look at the key, and we can see that the key consists of the key of the parent entity with the key of the child appended to it, right? We have person Ethel, person Jane. This uniquely identifies this entity and tells us that it's a child. And then if we look at the entity group, right, we can see that the entity group and the key are not the same. This is therefore a child entity residing in the same entity group as Ethel. So that's how we see ancestor sort of played out in the physical model. The data store also supports heterogeneous property types. On the Ethel entity, we can see that the type of the age property is an int64. Ethel is 30. But Jane here is a little bit younger and maybe likes to describe her age in terms of half years. So we can represent that as a double, right? Because the data store is schemaless, there's no problem representing age as an int in one record and age as a double in another record. We also support multi-value properties. Ethel, this 8.5-year-old, has multiple best friends, right? We can store this in a very natural way in the data store. If you've run into this situation with the relational database before, you usually have 2 choices. You can either sort of break that multiplicity out into a separate table, or, and I'm guilty of having done this in the past, you can put data in sort of like, you can add some logical structure there where you can separate the data with commas, and you can say, okay, well, yeah, it's a multi-value property. I can't query for it because the querying mechanism doesn't understand the implicit structure that you've baked in there, but it is a way to sort of fake multi-value properties. With the data store, you can do this in a really natural way. It works great. And then the final thing I want to point out is that Jane, this child record here, has a grade property. Jane's parent, Ethel, doesn't have a grade property. So it's perfectly acceptable for one entity of type of kind person to have a certain set of properties and another entity of kind person to have a different set of properties. I want to talk about transactions a little bit. This is going to play an important role in the discussion of soft schemas and JDO JPA persistence mapping that's coming along. So I want to make sure everybody has a good understanding of what data store transactions are and how they work. I described the entity group before as sort of a partition key, and one of the reasons this is important is that you can only transact on entities that belong to the same entity group. So if you look at the example here, we can see that we have Ethel and Jane belonging to the same entity group, but then person Max here belongs to a different entity group. What this means is that I can make an update to Ethel, and I can make an update to Jane, and I can have that update succeed or fail atomically. But if I add an update to Max into that mix, and I try to commit the transaction, I'm going to get an exception back, because I'm trying to perform an atomic operation that spans entity groups. So soft schemas. Here's the definition. A soft schema is a schema whose constraints are enforced purely in the application layer. What do I mean by that? Well, this is a scenario where your application's expectations of the structure and the validation that's been applied to the data, that is the schema itself. And when you're working with a data store like the App Engine data store that does not have a schema baked in, this can be really valuable, because this takes you from an area where perhaps you're used to having the database do a lot of this validation and provide this structure for you, into an area that looks a little bit more familiar, right? You have to give up some of that structure when you move to the App Engine data store. But if there's some way to implement a soft schema on top of it, then you're back in the area where things look maybe a little bit more like what you're used to. So we actually get some nice things out of a soft schema. First and foremost, well, when you don't have a schema at all, if any of you have worked with sort of the low-level API in the data store, you've probably seen how easy it is to rapidly prototype an application that requires persistence. And that's great. That rapid prototyping is great. But I'm a Java guy, and I love type safety. So I would like to have the ability to do that rapid iteration and that rapid prototyping, but do it in a type-safe way. So having a soft schema where I actually have some structure to my data encoded in the application, that's going to give me that type safety, but still give me the flexibility to do that rapid prototyping. The other argument I want to make in favor of soft schemas has to do with sort of consistency throughout your development process. I've been on projects before where we're developing a web application in Java, we're using a relational database as our storage solution, and we typically find ourselves doing things two different ways. Right, so what goes into developing this application? Well, we need to write code. We want to have unit tests. We want to have different deployment environments, development, QA, staging, integration, production, and so on. And we find ourselves sort of replicating that process for Java, and then we find ourselves replicating that process for managing the database. Right, we have to manage our seed data. We have to manage our schema, and then we have to figure out a way to unit test that migration. That migration code that we've written. And so it's these parallel ways of accomplishing the same thing. And I'm not saying it's not possible to get to a point where you can do that efficiently. What I am saying is that it takes effort, and oftentimes you end up maybe cutting corners on one of those sides, and it's usually on the database side. If you are using a soft schema, you have the opportunity, and in a sense it's sort of a forcing function. It forces you to do everything related to managing the structure and the content of your data store the same way. Right? So you can write your code, in Java. You can write your business logic in Java. If you're using GWT, you can write your front end in Java. And now, of course you could do this before, but now we're sort of forcing you a little bit to manage your data in Java. The benefit you get from that is you're doing everything the same way. And I think there's a lot of benefit to consistency in a software development lifecycle. So how are we going to implement a soft schema on top of the data store? Well, it turns out in the Java world, we are fortunate enough to have not just one, but two persistence standards. We have JDO and JPA. And just a quick show of hands, who here is familiar with either JDO or JPA? Okay, so a fair number of hands. Really quick definition, or really quick explanation of JDO and JPA. These are transparent persistence frameworks. The idea is that you take your model object from your application. Let's say it's a bug tracking system, so you might have a bug object, and you provide some metadata for that bug object that describes how that object is supposed to be persisted. And typically you provide that metadata either using annotations or XML, and then you have this framework behind the scenes that knows how to interpret that metadata and take that object and persist it in some sort of data store. So JDO and JPA are both Java persistence standards for getting this type of transparent persistence. Now what I'm going to argue is that JDO and JPA effectively give you a soft schema definition. How do I know that they do it? Well, if you've used pretty much any ORM out there, if you've used Hibernate or TopLink or Data Nucleus, they all come with these round-trip tools, right, that can take your Java objects that you've provided the metadata for and spit out a relational database schema based on that metadata, right? So if those round-trip tools exist, if there's enough information encoded in the metadata that you've provided to generate a relational database schema, there must be enough information in that metadata to define what the structure and the constraints that your application expects. So JDO and JPA, just by using them the way that you would normally use them, are going to give you this additional structure to your application, which is going to turn the data store from something that maybe looks a little bit different because it doesn't have a schema into something that looks a lot more like what you're used to, something that we can call them tables and columns. We know from looking at the physical model, which we already went through, that they're not actually tables and columns, but you can draw that connection there. The other great thing that we get from this, beyond the soft schema, is we get to write our persistence code using established Java APIs. And there's huge value in this. If you already know how to use JDO and JPA, and you understand what the interfaces are, that's one less thing for you to learn when you're trying to build an application on App Engine. That's hugely valuable. Another great thing is if you've used JPA or JDO recently and you use an IDE, there's built-in tooling for these things already, right? If you create an entity in Eclipse or IntelliJ and you set it up incorrectly, you're going to get the little red squiggle that says, hey, you're doing it wrong. Now, it takes a long time. It doesn't take a long, depending on the technology, it can sometimes take a while for sort of the tooling ecosystem around a new technology to get built up. But because we're using things that have already been around for a while, a lot of that tooling exists. That's, again, hugely valuable. The reason that I'm most happy about this, though, is when it comes to porting. It's really important to us on the App Engine team that you have the flexibility to take your code someplace else if App Engine isn't meeting your needs. We obviously want you to take existing code and bring it on. We want you to try it out. But it's important to us that you not feel locked in once you're there. And using these existing persistence standards really goes a long way towards making it easier to take your code someplace else. That really is important to us. And we're going to go through some examples later on in the talk for some strategies of how to do that. So it turns out, we looked at JDO and JPA. We said, okay, this is great. We can get a soft schema from this. This is going to make the data store look a little bit more familiar to people. We're going to get the established APIs. We're going to get the tooling. It's going to be easier to port. But will it work? Right? These are these existing standards, and they were not designed with platform as a service in mind. Right? They did not have the App Engine data store in mind when they were designing these specifications. So, does it actually line up? And the answer is mostly yeah. it's a pretty good fit. It turns out the specifications are mostly mappable to Datastore features, and that the Datastore features, some of these interesting features that I described a few minutes ago, those features are actually mostly mappable to the specifications. So we're going to go through some examples of how to surface some of these Datastore-specific features through Java persistent standards. So here's an example of how we can do an ancestor query using JPA. You'll notice we have, so this is a JPA entity here. Here's an address, and let's assume that an address is owned by a person, right? So we have a one-to-many relationship from person to address, and I haven't shown you the entire class here because it would be too much code to read. But we do have a key, right? This is an App Engine-specific primary key class, which you can use. You don't have to use it, but in this case, just for clarity, we're using it. Here is a key that uniquely identifies the person that owns the address. If you were modeling this in the relational database world, you could think of this as a composite primary key. By using this extension annotation, which is not an App Engine-specific annotation, this is actually something that Data Nucleus understands. By using this annotation, we can tell the App Engine JDO JPA implementation, hey, this is a parent. This is part of an ancestor. And when you query based on this field, we can recognize that and say, oh, the field that they're querying by is a parent primary key. Let me execute an ancestor query. And so you can see that this query down here, which is just standard JPA query, there's nothing special about it, but we're interpreting it in a special way because of this annotation. Filtering by multi-value properties. This is a really, really nice and natural way to express a query. So now we're looking at a JDO example. Where we have a person, and a person has some number of hobbies. And we can just say, select from person where hobbies contains yoga. Give me everybody who considers yoga a hobby. This works, and this is a really natural way to express one of the nicest features that you get from running on the Datastore. Transactions. This is a little bit trickier. The API for transactions in JDO and JPA is a nice fit with the API for transactions in the Datastore. It's basically begin, commit, or roll back. So syntactically, we're in good shape, but semantically, it gets a little bit more difficult. And the reason is because of the nature of transactions, which I described before, how with the Datastore, you can only transact within an entity group. If you're coming from the relational database world, you're probably used to global transactions, where you can update any record in your database, and you can say commit, and that's totally fine. So how do we bridge this gap? Well, we're going to look at some strategies later on. I just want to sort of point out that there is this difference here. But the other thing that I want to point out is that the challenge that we're facing right here is really no different than the challenge we face when we are sharding our data anyway. So if you are splitting your data across multiple relational databases, you are going to face a similar challenge. You don't have global transactions anymore because you have data that lives on this server and you have data that lives on this server. So you can't just do one global transaction here and expect to be able to atomically update something over there. What's the solution? It's two-phase commit. And as some of you might have seen in Dan Wilkerson's talk yesterday, he has a working algorithm for two-phase commit on the App Engine Datastore. So the problem is similar to what you get with horizontal partitioning. The solution is similar to what you get with horizontal partitioning. Let's talk about relationship management. And this is not a self-help course. We're talking about JDO and JPA here. This is some of the most powerful stuff that, and I'm going to use the word ORM. Right? JDO and JPA are essentially standards for ORMs, and the R in ORM stands for relational. And that's confusing because we're not actually talking about anything relational here, but it's a common term. So JDO and JPA are standards for ORM. And I've spoken with a sizable number of developers over the years who say, I don't like ORM, I don't like giving up the control over what gets fetched and what gets updated. And I totally understand that. It is fairly easy to have a lot of things going on under the hood with an ORM, and some people really want to stay close to the metal. The point that I want to try to make here is that JDO and JPA have a lot of value beyond sort of all the magic that it will do under the hood related to relationship management. And by relationship management, I'm talking about the fact that you can declare a one-to-many relationship and you can just sort of add something to a collection, and because it's reachable from something that's already persisted, it will automatically get written to the data store. The fact that you can touch some object which hasn't been loaded by the data store yet, and the framework will say, oh, this thing hasn't been loaded, and it will pull it into memory. Right? That's the kind of stuff that people can easily get tangled up in. And the point that I want to make is that you don't have to take advantage of all of that stuff to find JDO and JPA useful. The biggest benefit, I think, that you get from these technologies is the fact that you have a centralized mapping for the metadata of your model objects. Right? It's not scattered around your application in a bunch of properties files that have SQLs or that have SQL statements or Java files that have JDBC code. Right? It's centralized either in XML metadata or in annotations on your object. That is a big maintainability win. And just using that alone, right, you get the soft schema, you get the familiar APIs, you get the tooling, you get the portability, and you don't even have to touch the relationship management stuff. Now, that said, I also want to encourage you to try and take advantage of the relationship management stuff. And the reason is that on the App Engine data store, this becomes more important. It becomes more important than it might be if you were using a relational database. The reason is that relational databases have foreign key constraints. So when you have a one-to-many relationship between, say, person and address, and you want to store the primary key of the person that owns an address on the address table, you have a foreign key there. And if you add something to that person ID column on the address table that, if you set it to null and it's not nullable, or you're referencing a person ID that doesn't exist, the database is going to catch that mistake and say no. But the App Engine data store is schemaless, right? We're going to be more flexible about things. But if you let JDO and JPA take care of the relationship management, they're going to make sure that these things get set properly. Now, you can write this code yourself, and typically what happens is you write it yourself once, you write it yourself a second time, you write it yourself a third time. All of these different situations, you probably get them mostly right. And then at the fourth time, you say, man, I'm sick of writing this code. I'm going to write a small framework to take care of it for me. And the next thing you know, we have our 18th ORM that's available on SourceForge. So letting the framework manage relationships for you is particularly important when you're using the App Engine data store because there are no foreign key constraints. The other big win, and for me, this is the killer feature. I'm going to try to convince you that this is cool and useful. The killer feature here is transparent entity group management. Deciding what entity groups your objects are going to reside in is one of the most important design decisions that you're going to make when you're building an App Engine application. And there's some tension here, right? It's tension between write throughput and atomic updates. There is a limit on how often you can update something that lives in an entity group, right? It's approximately 1 to 10 writes per second within a single entity group. But on the other hand, the only way that you can update multiple objects atomically is if they live in the same entity group, right? So you might say, okay, well, I want to have global transactions, so let me put everything in my application in the same entity group. Okay, but now you're limited to 1 to 10 writes per second, and you're going to get lots of concurrent modification exceptions. So there's a balancing act here, and only you know what the right balance is. Once you've decided what that balance is, it's up to you to implement that in your application to make sure that these objects actually go into the correct entity groups. However, if you use the relationship management functionality that comes with JDO and JPA, we are going to be able to assign objects to appropriate entity groups on your behalf. So when we talk about relationships, we typically refer to them as either owned or unowned. And by owned, I mean the child object doesn't make sense without its parent. As an example, think of a book as a parent and a chapter as a child, right? It doesn't make sense to have a chapter without a book. An unowned relationship, on the other hand, is something that can exist perfectly fine without an owner, right? You might have a person and you have a car, and you might have an association between a person and a car at some point in time, but the person could go away and the car still exists, right? It still makes sense, and maybe somebody else owns it or maybe nobody owns it. But we could describe that as an unowned relationship. So the way that we make transparent entity group management work is we let ownership imply entity group co-location. So here's an example. And this is a JPA snippet where we have a person entity with a one-to-many relationship to pet. And then down below, we show you what the physical model looks like when you set up your model this way. And I want to point out that this model, this is standard JPA code, right? There's nothing about entity groups in here. We've just said at entity, at one-to-many. But since at one-to-many tells us that this is an owned relationship, we can use that information to automatically place pet in the same entity group as person. So on the left here, we have person, which is the parent, and then on the right, we can see that this pet number 18, its parent key is this person. They're sitting there in the same entity group. So this works great. This is a powerful way to take one of the newest entity groups are a feature of the data store that you need to understand in order to be successful building your application. But this is a really nice way for us to give you some sensible default values for it so that you don't have to contend with it quite as much. So again, this is along the lines of taking something that's maybe not quite so familiar and folding it in to a concept that you already understand to make it a little bit more familiar. So why does this say owned one-to-many today? Well, let me show you what I want the future of owned one-to-many to look like. You'll notice that there's an additional property on that person entity there, where the parent actually has a reference to the thing that it owns. Why is this important? Well, I can think of two reasons. First off, if the parent has a reference to its child, that opens the door to a certain subset of join queries that you can't otherwise express using the data store. This lets us issue a query that says, give me all people, or give me a person older than 30 that owns a particular pet. That is a type of join query that is otherwise difficult to express. The other thing it does is open the door to some optimizations. Wouldn't it be great if you had a person object loaded in memory, you haven't loaded the pets owned by this person yet, and you can say, hey, person, how many pets do you have? If you have all of the pets that the person owns as part of the person entity, you can answer that question without making another trip to the data store, issuing another query to get that answer. If you don't have that information, it's absolutely another trip to the data store. So there's some nice optimizations that this enables for us. So what's stopping us? Well, there is this interesting constraint in the data store that you can only update an entity once in a transaction. And, to be perfectly frank, this is an implementation detail that has sort of found its way out to you. But it's something that we have to contend with. So let's think about what would be involved in getting that child key onto the parent. First, let me explain the data store can do ID generation for you. But the only way to get the data store to generate that ID for you is to actually save the object. It's sort of like an identity column in MySQL, right, where you insert the record, and when it comes back, it has that value set. So we need to get the child key on the parent, right? Well, so in order to get that child key, we have to save the child. That's the only way we're going to get that ID generated. But we need to make sure that the child resides in the same entity group as its parent. And the only way to get a child into the same entity group as its parent is to construct that key using the key of the parent. So we need the key of the parent before we can save the child. That means we need to save the parent first. Okay, so we can save the person, we can get the person key back, we can use that person key to construct the child key, we can then save the child, get the child key, and then we can set it back on the person and we can save it. Except that's the second update to the person in the same transaction. So we can't do it. What we need is a getNextID operation on the data store, which fortunately we are in a good position to add, but it's not there yet. Once that operation is available, we can solve this problem, right? We can ask the data store for, hey, give me the next ID for a person. Hey, give me the next ID for a pet. Now I can take that pet ID, I can set it on the person, I can save the person, I can save the child, and I've got what I want by only updating the person once in my transaction. That's great. The other thing that it's important for us to solve, and I'll be honest, I don't have as clear a picture of how we're going to solve this as I do for this other scenario, is unowned relationships. So we've talked about how JDO and JPA, we can use ownership to imply co-location within an entity group. Well, JDO and JPA also provide a really nice way to express unowned relationship, using the objects themselves, right? Instead of just having a key, you get the object itself as a member to model that association. So we can use an unowned relationship as a queue to store these entities in separate entity groups. The issue here, though, is, again, you can only transact across entities that live in the same entity group. So if you had a person and you had a car and you had an unowned relationship between person and car, but they live in separate entity groups, and you start a transaction and you load the person and then you load the car, you get an exception because you're trying to do something transactionally across multiple entity groups. So there's a danger here of exposing something that everyone expects to work in JDO and JPA, and it looks normal, except when you try to do something totally normal and obvious with it, it doesn't work. That's dangerous. That's not something that we want to do. So I don't know what the right answer here is. We may need to come up with something. The other thing that it's important for us to do with the JDO and JPA implementations is achieve feature parity with the Python Datastore API. Those of you who are familiar with both may have noticed that with Python, it is possible to do a not equals query, or it is possible to do an in query, right? Select star from person where favorite color is in blue, yellow, red. That imbalance isn't just because we need to flip some bit on the Java side. The data store itself does not natively satisfy those types of queries. What we did for Python, because we had a little bit of extra time, is we implemented those, we call it in user land. It's sort of part of the API layer itself. There's no reason why we can't do that for Java. We just haven't done it yet, but that's an important step. And then our JDO and JPA implementations are going to be a lot more filled out. So let's talk about some strategies for migrating existing code to App Engine. And I know I hammered this point home at the beginning, but I'm going to say it again. The data store is not a relational database. It is not a drop-in replacement for a relational database. So even though we are talking about Java persistence standards, which are oftentimes used to persist things in relational databases, that does not mean that the App Engine data store is a relational database. When you want to bring code over, you're going to need to do a bunch of analysis of your application. You're going to want to look at your list. You're going to want to look at your use of primary keys. You're going to want to look at your use of transactions, of queries, of data, of vendor-specific features. And you're going to need to come up with a plan. You're going to need to think about data migration as well. I really can't emphasize this point enough. Data migration, I don't think I've ever given an estimate for data migration that was within 3x of what it actually ended up being. It's just one of those things that always ends up harder than you expect. So don't forget about the data migration. You may notice that, and we're going to get into some more specific advice, but the advice that I'm giving so far, there's actually nothing App Engine specific about this. If you were switching between any two databases, these are exactly the sorts of things that you would want to look at and think about. So let's talk about primary keys in particular. If you have single column primary keys that are numbers or strings, varchars, that's going to work pretty nicely. There's a very straightforward way to map that on. Composite keys with the data store, we just have a notion of a key, but it is sort of a composite key because we do have a notion of ancestor. So if your composite key can be thought of as an ownership chain, like a single strand ownership chain, then you can take your composite key and you can map that to ancestors and entity groups. That works pretty nicely. So we have an example here of a pet object where we have a composite primary key consisting of the pet ID and the person ID. And then over here on the right, we can see that this maps to an ancestor chain where the top-level element is the person and the child element is the pet. For mapping tables, you could think of a mapping table, and in many cases it contains a composite primary key where there isn't a single chain of ownership, right? If it's a mapping table, chances are it's owned by multiple things. So this fits really well with multi-value properties. So in this example, we have a friendship table modeling who is friends with who, and we can see that person 8 is friends with person 32 and 34, and we can translate this nicely to a multi-value property called friends on a person entity, and it has multiple values. Person 8 is friends with person 32 and 34. Now, you may look at this and say, wait a second, that's only a unidirectional relationship. What if I want to model the fact that person 32 is friends with person 8 and that person 34 is friends with person 8? You can do that. It will work okay, but there are some more complicated things that you need to start thinking about, particularly related to transactions, right? Person 8 and person 32 are in separate entity groups. And let's say I want to establish a bidirectional friendship relationship between them. That means that I need to update person 8 in one entity group and person 32 in another entity group. And if I want that to happen atomically, now I'm in a tough spot, right? Because they're in different entity groups. So now it's up to me to decide, well, is it okay if the first one succeeds and the second one fails? Do I want to roll the first one back with a compensating transaction? Do I want to have something sweep through and clean it up later? There's a little bit more to it. Which brings us nicely to our next subject. What's involved in porting on transactions? We talked about the mismatch before, how with the data store we have transactions across entity groups, and with relational databases, if we're not partitioning our data, we're typically used to having global transactions. So the strategy here is you want to identify the roots in your data model, right? And if you're building an online service, the first place I would recommend looking is user, right? Can you hang all of the data off of a user and get reasonable write throughput? If that works, you're in good shape. It's not going to work for everybody, but that's a good first place to look. Once you've identified the roots in your data model, you're going to need to find the operations in your application that transact across multiple roots, right? Again, these are the scenarios where the fact that transactions apply to a single entity group, these are the scenarios where that is going to force you to do something a little bit different. Well, what's it going to force you to do? Well, it really depends on the specific situation. You need to look at these scenarios and figure out what partial success means. Is it acceptable? In the bank account transfer example, probably not partial success is probably not acceptable. So what do you do about it? Well, one option, and I wouldn't expect anybody at all to be happy about this, but one option is to say, well, I'm not going to support this anymore. You're going to just change the functionality of your application. Better examples, if partial success is okay, right, the fact that your first update succeeds and the second one fails, and maybe there's a little bit of inconsistency there, that might be okay, in which case disable your transaction and move on to the next one. You're in okay shape. If that's not acceptable, then again, your options are implement a compensating transaction, right? First update, second update fails, try to roll back the first update. You can do that, or again, a background process. These are the options. These are the types of things that you need to think about. For queries, again, you're going to need to analyze your usage. And the general guidance that we give people when we talk to them, when they're coming to App Engine from the relational world, is shift processing from your reads to your writes. Right? So we don't support join queries, but denormalization works great. Right? It's another way to get the data you want. So in this particular example, we have a typical join. Select star from person A. We're going to join on the person column across person and A, and then we're going to filter on some property of person and some property of address. Typical join query. If we denormalize, right, storing information about the address on the person itself, right, we're duplicating that data, then we can issue a much more straightforward query. So we've shifted the processing from writes, right, because now when we write a person, we also need to write information about the address. When we update the address, we also need to update the person. We've duplicated that data. So we're pushing the processing onto the writes. But that's going to allow us to do a really efficient read. For other operations, things like toUpper, for example, right? You want to do a query, and you want to match on the uppercase version of some column that's stored in the data store, some property that's stored in the data store. Well, one solution there is to store multiple versions of that string, right? You store it in the natural form, the one that you want to actually show to your users in your UI, and then you store it in the uppercase form, which is the one that's going to support the query. Yes, it's duplication, but you're pushing the processing onto the writes in order to execute a more efficient read. Let's talk about the easier direction, migrating things off of App Engine. Of course, we're sad to see anyone go, but we know this is going to happen, and it really is important to us that you feel like you can take your code someplace else. So the reason that this is the easier direction is that when it comes to persistence, App Engine is generally more restrictive than the environment that you're probably porting to, right? And the environment you're probably porting to is a relational database. So when it comes to queries, right, the App Engine data store doesn't support joins. Relational databases typically support joins. It's more restrictive. You're using a subset of the query functionality of a relational database when you're building on the data store. Similarly for transactions, entity group transactions are more restrictive than global transactions. Multiple updates. App Engine data store, one update per entity. In a relational database, you can probably update an entity as many times as you like. So it's more restrictive. So the fact that you have been developing against a subset means that when you take it to this other place, more things are going to work. That's good. We're happy about that. The biggest thing that you're going to need to decide when you're building your application on App Engine is what portability means to you. And once you've decided what it means to you, then you need to decide how important it is to you. So there's multiple valid definitions of portability, right? One definition could just be, I want compile time portability, right? I don't want to have any Google App Engine import statements anywhere in my code, right? That doesn't necessarily mean that you can build it and just deploy it into some other environment, but you don't have any compile time dependencies on App Engine. That might be your definition of portability. You might have a definition that says, not only do I not want to have compile time dependencies, I want to be able to just change some configuration file and be able to deploy that into some other environment. Again, that's a perfectly reasonable definition for portability. It might be that you want to have a single binary that you build it, you deploy it to App Engine, you deploy it to WebSphere, and you do nothing to it. That's another definition of portability. And depending on which one of those you choose, or you may have some other definition, that is going to have a lot of impact in how you design things. The nice thing is that no matter what your definition is, you've already sharded your data model. And if you happen to be an application that has lots and lots of data, and you would need to be horizontally partitioned if you weren't running on App Engine, then you've already done the hard work. And that's great. So let's look at a portable model object, right? Here's a root object. It doesn't have a parent. This is a JPA entity. It's a book, right? There's a primary key. It has a title. And on the left, we can see what the physical model looks like in the data store. We've got our kind, our entity group, and key. Entity group and key are the same. That's how we know this is a root entity. And there's the title. And then on the right, we have our simple book table, which has its primary key and a title of Vineland. For child, yeah, it looks a little bit uglier. But we do have compile time portability here. We have added this data nucleus specific extension. It's not an App Engine extension, right? To use this extension, this is actually something that data nucleus gives you. We can say, hey, store the base 64 encoded representation of the key in this string object. The reason we need to do that is because this one field needs to uniquely identify a chapter, and a chapter is a child object. And for child objects with App Engine, the parent primary key is part of the primary key of the child, right? So we need to embed additional information in there. So we're saying we're declaring it as a string, and we're telling data nucleus, hey, I want additional stuff in here. But then we're also declaring this additional property, a parent key, right? This is similar to the thing that enables you to do ancestor queries. We've got this additional property that says, hey, I want to expose the primary key of my parent. When we translate this to the physical model, on the left-hand side, again, we have a typical child object here, right? The key contains the parent key and the child key, and then our properties, 23 pages. And then here's our chapter table with our composite primary key consisting of the ID of the chapter and the ID of its parent, and then the columns. So the key things that I want you to take away from this talk as we're wrapping up. First and foremost, the App Engine data store simplifies persistence. It simplifies the development of your application. You get the rapid prototyping. You get the rapid type-safe prototyping if you're using JDO and JPA and implementing a soft schema. And it simplifies the management of those applications. And yes, it simplifies the management of scalable applications. But again, scalable, every application needs to scale to a certain degree. It just depends on what that target is. You can use JDO and JPA to implement a soft schema. This is going to take something that looks a little bit unfamiliar, a schema-less data store, and establish the structure on top of it to make it look a little bit more like what you're used to. When you're thinking about moving applications onto App Engine, denormalization is not a dirty word. Do not be afraid to duplicate data. This is a great way to be able to execute complicated, efficient queries on App Engine. And finally, when you're going the other direction, taking your code someplace else, plan for portability. Decide what your definition of portability is, and then stick to it, and you'll be in good shape. And with that, I will be happy to take questions. Here's a couple of links, information, ways that you can get more information on App Engine. And please, if you have feedback for the talk, visit that link down there at the bottom. Thank you very much.
Hi. Thank you for the talk. It was very informative. What I'm taking away from this is most applications, you could build them on a relational database or an App Engine if you kind of think about it the right way for the underlying platform. Could you identify some kind of criteria where you'd say if A, B, and C are true, then you're really in the sweet spot for relational database and relational data models making your life easier, versus if X, Y, and Z are true, you're in the zone where the App Engine model is going to make your life easier and relational is pushing a stone uphill?
Okay. So first and foremost, if you build on App Engine, the whole management side, the operational side of dealing with persistence, that's always going to be better. So, if you can get there, the management side is pretty much always going to be better, right? You don't have to manage your database servers anymore. That alone is a big win. But, your question is, when does it make sense to sort of work hard to get to that point? I would say, this process of looking at your data model and identifying roots. If you look at your data model and you can't find any roots, right? Everything is just pointing every which way. That is going to be a challenging port, right? Because the transactional functionality, and to a certain extent the querying functionality, sort of assumes that you can slice your data, that you can partition your data. So if that part goes badly, then you may not be in a good spot. If that part goes really well, then I would say, go forward. Wait until you hit the next bump. I can't stand up here and say it's always going to be straightforward. It's always going to be easy. What I'm hoping to do is get the conversation started about what are the common strategies, what are the common patterns. And the product's been out, I think, 8 weeks now, so we're still pretty young. But one of the things that I'm really hopeful for is that we see the community, and I'm happy to kick this off, but I'd like to see the community start putting together essentially a cookbook of what types of things we should be looking for and how to move those things over. Yes?
Thank you for the talk. I saw another talk yesterday on distributed transactions.
Yes.
And I was wondering if you had any thoughts on that and how it applied to...
It applies really nicely. So I saw Dan Wilkerson's talk yesterday too. For those who didn't see it, there is an existing algorithm for implementing distributed transactions on top of the App Engine data store, and it was done entirely in user land, like above the low-level data store APIs, which is why Dan was able to do it, because he doesn't work for Google. If you really need global transactions, then this in theory, this will help. So I have not tried out his implementation. So I cannot say either way sort of what the additional storage cost is, what the additional performance cost is. Based on what I know of it, there is definitely some additional storage cost. There is definitely some additional performance cost, but I can't say to what degree and how those things are affected by data volume, by the size and shape of your data. So we're going to have to see. I'm really looking forward to that code being made available, and I hope people try it out. It may work really, really great for some people. But yeah, keep an eye out for it, definitely. Yeah?
Hi. To what extent have you guys done work on kind of prefetch rules and hints for the implementations to be able to load kind of large graphs in one go rather than kind of ripple loading?
Yep. In one go means something different for the data store than it does for a relational database, right? If you're using JPA and you say, I want you to fetch this relationship eagerly, that typically translates to a join, right? But the App Engine data store doesn't support joins. So even if you said, I want it eagerly, that would just result in multiple queries done up front versus multiple queries spread out as the thing is used. I'm not sure how much value there would be in sort of executing multiple queries up front versus executing multiple queries as needed, right? Like the optimization is from the join.
Yeah, what I was getting at was not the API side, but the back-end side. So I guess another way of asking, are there any plans in the roadmap for supporting a means to be able to prefetch and do kind of bulk operations like that? Whether you call it a join or it's some other...
Okay, so we already support batch gets. We already support batch inserts. But for queries, we don't have any immediate plans to allow you to issue a query that will... I don't know how else to describe it other than a join query. I mean, that's
Sure.
typically what you end up expressing. But for individual records, there are batch operations available already. We have not yet exposed those batch... Actually, not true. Batch gets are exposed in JDO and JPA. The batch puts, even though the interfaces, they have things like make persistent all or persist all, they do not yet take advantage of those batch operations, but that's just because we haven't implemented it yet.
Okay.
So we'll get better with those, but for the hard stuff, it's tough to say.
Thanks.
Yeah.
You talked about the suggestion of making user your entity root so that you could have transactions among any of the children underneath there.
Yeah.
But that seems, there must be performance implications if suddenly I just have that up here and everything grows underneath that as children. There need to be some downsides. So is that really that easy? Or what are some of the penalties, performance or space or otherwise?
So it depends on the access patterns of the data, right? If this is email, typically you are accessing your email. You are reading email, you are writing email, and chances are other people are not, hopefully, reading and writing your email, which means that you don't have to worry quite so much about concurrency, right? Because it's you, so you could be on multiple computers at the same time, but chances are it's just you. And in that sort of model, then yeah, user is a great choice. But If you have something that really does require a lot of concurrent modification, then that's when you need to really think harder. So yeah, I mean, the reason I say use user if it works is because it's it's part of a domain that is commonly there, and it might work out great. Like that's sort of like a best case scenario for you, but it may not be the average case. Yeah. Question?
Yeah, it's a question again about distributed transactions.
Yeah.
In the future, do you plan on using distributed transactions under the hood inside the JDO or JPA so that you can support some of these other queries that you can't support joins and so forth? So I don't have to worry about distributed transactions.
Right.
The library would do it for me.
Right. So if we can get the throughput we need from distributed transactions, then I would absolutely want to bake them in a way that meant you had to think about it as little as possible. But again, it starts with what impact it has on the size on how much data is stored and the performance implications. And I'm in no position to guess.
Yeah, I haven't used your storage framework, but what kind of performance can we get? How many writes on a given, is it what you call entity group?
On a given entity group, it's one
for a small object,
So the rule of thumb is you can expect 1 to 10. You can expect to be able to execute 1 to 10 writes per second on an entity group. Next question.
So I've been converting a Batis application in the last 8 weeks, at least the DAO layer over to App Engine.
Yep.
And the existing data model has a few unowned relationships and many-to-many relationships, and I've been trying to isolate them and whatnot. I noticed today you said you're not as of yet allowed to do inquiries. So with a situation like many-to-many, what kind of approach would you take to, get a collection of something only given a collection?
Yeah. So if I'm understanding your question correctly, multi-value properties can be really helpful here, right? If you have a many-to-many and you have the list of keys on one side or even on both sides, then if you think back to that contains example that I showed where I said, show me everybody who considers yoga to be a hobby.
Right.
That query will work great for your scenario based on those keys. You can say, show me all of the people who consider this person a friend, right? That will basically give you all of the people that have this particular key in that collection.
Right. This is sort of a bidirectional situation.
Yep.
where you really don't have, you can't really trust that you'll be able to write both at any given time. Well, you can trust one side but not the other.
Yep.
Is there a way of like hashing or caching or something like that you could?
I'd have to think about it more.
Oh, okay, thank you.
If you post your question on the message groups, I will think about it more, and I'll try to get you a better answer.
Thank you.
Yeah.
It's kind of a follow-up question to his question. For migrating something like Hibernate or Ibatis that has support for JPA but also has its own proprietary annotation and query language,
Yep.
if you were to move to Google App Engine and migrate away from the annotations of whatever ORM tool you're using to JPA,
Yep.
is there any options for a neutral query tool for building up, or is it part of JPA itself, or like is some good way of having criteria query for Hibernate and something on the App Engine side? You can still use Hibernate, but if you wanted to use something more neutral in case you wanted to pull it out later and switch to something else.
I'm not sure I completely understand. So you want to leave your Hibernate specific code
Oh,
in place?
You don't want to, but you kind of have to unless you want to migrate to something else, or if you're going to want to get away from conventions of Hibernate because it keeps you thinking in Hibernate versus going to something more neutral.
The migration path I would recommend there is, as you said, right, Hibernate is a JPA implementation. Right. So I would migrate up to JPA, still use Hibernate, right? Get to that point, and then move over.
Right.
Like I think that's how I would approach it. I can't think of. I wouldn't recommend a shortcut.
Okay.
Yeah.
Okay.
Yeah.
Thank you.
Sure. Okay. Last two questions, and if there are people here who have questions but you haven't stood up, there's a fireside chat in the Fireside chat room with the App Engine team, like right after this. So just come on over there and you can ask more questions. Yes.
In the JDO or JPA implementation, the data nucleus implementation, does it do dirty field detection and only write the dirty fields when you're doing an update, or does it need to write the whole entity?
So data nucleus does dirty field detection. And data nucleus then tells the App Engine plugin, hey, write just this one field, and then we write the entire entity, because the Datastore does not support updates at that level of granularity.
Okay, thanks.
Yep.
Just to be a bit more clear, you did talk in JDO, JPA addressing the ownership. So a person owns multiple pets, and a pet can only be owned by one person. But how about a situation where the entity group is actually like an intelligence organization? So you have an entity group for KGB and one for FBI.
Yep.
And then you have James Bond, Bruno, Borat. They're all spies. And then you have top secret documents, maybe 10 of them. Can you, within a transaction using JDO or JPA, associate Bruno with the 3 documents he just checked out, and Bond with the 2 documents he just returned, and do that all within JDO, or do I have to go to a lower level?
You can do it all through JDO, but you will have to explicitly define your model objects containing keys of some of these other objects as opposed to the type of the object
so
itself.
You're saying, like, for example, the documents can only be checked out by one person. So I guess that'd be a traditional foreign key in a database. But for the person owning the checking out the books, you'd have a multi-valued property that's just a list of the things they have. And JDO can handle that out of the box.
JDO can handle that. JDO can handle that fine. You just have to take care. So you've asked an interesting question. You know, we use ownership to imply entity groups, but that is not the only way to set up entity group relationships. It's just a nice default value. So it is possible to have documents as part of an entity group and people as part of the same entity group, and have an unowned relationship between those documents and those people, and have those documents and people still reside in the same entity group.
And JDO can handle establishing the relationships and de-establishing them just fine. Well, you know, I had kind of like a 0-1 in one way and then one-to-many in the other. How about from many-to-many? Just like, this spy is my friend, this spy is not my friend, keeping track of the social graph.
So anytime it is not an actual ownership relationship, you don't need to dip down to the low-level API. You can do all of this using JDO, but again, you can't define your model objects in terms of you can't define the relationships in terms of other model objects. You have to define the relationships, these unowned relationships, using their primary keys.
So it would just be you're storing strings or numbers instead of referring
you're storing
to the
unique
object.
IDs for these things, for the relationships. And that is not a limitation of JDO. That is a limitation of our implementation thus far. Right? So eventually we want to get to the point where you can say, yeah, this person has an association with this document, right? As opposed to this person has a field that happens to contain the primary key of this document, right? We want to get to that point. We just haven't done it yet.
And just to extend this a little bit more on the limitation, let's say we do have a social graph and this spy has many friends and these friends each have their favorite restaurant. And I want to find all the candidate restaurants of all my friends to decide where to go to lunch. So I can have to, in one step, get all my friends, and then I have to go query each of them, load each of them separately to get their set of favorite restaurants, and then form my unique set.
There's probably room for a batch get somewhere in there, where you can provide a bunch of IDs and pull back a bunch of records in one shot.
So I can get all my friends and then specify all my friends as in the batch and get back all their objects. So it's not a batch query, it's just a batch, like, get me people identified by 23, 29, and 34. Get me all of those people, and then you could... And the full entity that they represent, and then I can dive down and get the specific things I want. Thanks a lot.
Yep. I think we're out of time, but if you want to come over to the fireside chat, or we can just talk as we walk over there. But I think we're done up here. Thank you.